I am so glad you are here tonight, wherever you are in the world, whether you are tucked up under a warm duvet, lying in the quiet dark, or just settling in and hoping sleep will find you soon. This is your place. You are very welcome here. Tonight, we are going to drift together through one of the most beautiful ideas in all of science, the Goldilocks zone. That magical, almost fairy tale-like region of space where conditions are, as the story goes, just right. Not too hot, not too cold, but just perfect enough for something extraordinary to exist. Life. And I know what you might be thinking. Surely that is just a simple idea. A cozy little band of space around a star. But the more we look, the more we listen, the more we point our telescopes into the dark, the stranger and more wonderful it becomes. Tonight, I want to share some of that wonder with you, gently, no rush. We have all the time in the world. Before we begin, I have a small and gentle favor to ask. If you are enjoying Orbit into Sleep, a like and a subscribe really do make such a difference. It helps other restless souls find their way here just as you did. It costs nothing, takes a moment, and means the world to this little channel. Thank you so much. And if you feel like it, pop a comment down below and let us know roughly how many hours of sleep you normally get each night. We are all different, and honestly, it is lovely to hear from you. Right then, let us close our eyes, breathe in slowly, and let go of the day. Tonight, we travel to the edge of what we know in search of worlds that might be just right. Just right. The Goldilocks zone explained. There is something wonderfully childlike about the name, the Goldilocks zone. It sounds like the title of a bedtime story, which in a way makes it perfect for tonight. But the idea behind it is anything but simple. Scientists use the term to describe the region around any given star where a planet could, in theory, hold liquid water on its surface. Not ice, not steam, liquid water, flowing and present the way it is here on Earth. And water matters more than almost anything else because as far as we know, every living thing needs it. It is a solvent, which means it dissolves things, and in doing so, it allows the chemistry of life to happen. Nutrients move, cells function, organisms grow. Without liquid water, none of that begins. Now, the reason distance matters so much is simply heat. A planet too close to its star receives too much energy. Surface temperatures climb. Water boils away. A planet too far receives too little. Everything freezes. The water locks itself into ice and stays there. The Goldilocks zone is the band in between, the place where a planet might receive just enough heat to let water flow. But here is where it gets interesting and perhaps a little surprising. Distance from a star is only part of the story. A planet could sit perfectly within the Goldilocks zone and still be completely inhospitable, because the other thing a planet needs is an atmosphere, a blanket of gas thick enough to keep the pressure up. You see, water only stays liquid within a specific range of temperature and pressure. If the atmospheric pressure drops too low, water skips the liquid phase entirely. It goes straight from ice to vapor, never pausing to become the flowing, life-giving thing we need. Scientists call this the triple point of water, a precise set of conditions where all three forms, solid, liquid, and gas, can exist together. Below a certain pressure, liquid water is simply not possible, no matter how warm the planet might be. So habitability, that beautiful and loaded word, is really a combination of two things working together: the right distance from a star and the right kind of atmosphere to hold everything in place. What I find quietly wonderful about this is how fragile it all sounds. And yet here we are, on a planet that has been in its Goldilocks zone for billions of years. Liquid oceans, rain, rivers, life in enormous variety, filling every corner it can reach. We are the proof that it works. And tonight, as you drift, perhaps you might carry that with you. You exist because a planet found itself in just the right place, with just the right kind of sky above it. That is not nothing. That is everything. The concept itself is older than you might expect. The ancient Greek philosopher Democritus, more than 2,000 years ago, suggested that the cosmos was filled with uncountable atoms, forming countless worlds. He could not have known about stellar radiation or atmospheric pressure, but he looked at the universe and suspected it was full of possibilities. That instinct, it turns out, was right. Much later, in 1713, Isaac Newton did some of the earliest mathematical thinking about where around our sun a planet could hold water based on the sun's heat. And in 1802, a philosopher named Louis Claude de Saint-Martin wrote that Earth's particular position in the solar system seemed necessary for the life it carried, for its vegetation, he said. It took until the 1950s for the idea to become a true scientific framework. In 1953, two researchers working separately, Hubertus Struckhold and Su-Shu Huang, each began to formalize what we now call the circumstellar habitable zone, a defined, calculable region. A place you could point to on a diagram and say, there, that is where to look. And from that moment, the search began in earnest. Let yourself settle a little deeper now. Feel the weight of your body against whatever is beneath you. The room is quiet. The night is doing its gentle work. And we are just getting started. Worlds at the edge of the possible. Let us take a slow, unhurried journey now to some of the most extraordinary places astronomers have found. Real worlds, orbiting real stars, sitting within their own Goldilocks zones. Each one a candidate. Each one a question mark hanging beautifully in the dark. The first of these worlds came to our attention in December 2011, and it caused quite a stir. It was called Kepler 22b, and it holds a very special place in the story of our search for life beyond Earth. It was the first planet ever confirmed by NASA's Kepler mission to orbit within the habitable zone of a star very like our own Sun. Kepler 22b lives 640 light-years away from us. To put that gently into perspective, a light-year is the distance light travels in a full year, moving at nearly 300,000 kilometers every single second. 640 of those years worth of travel. It is almost impossible to imagine, and yet we found it. We saw its tiny shadow pass across the face of its star, and we knew something was there. The planet itself is larger than Earth, somewhere between 2 and 2.5 times our radius. It is not a rocky world the way ours is, at least we do not think so. It is more likely what astronomers call an ocean world, or perhaps a gas dwarf. A planet perhaps wrapped in deep water or swathed in thick atmosphere with no clear surface to stand on at all. We do not know for certain, and I think that uncertainty is one of the lovelier things about it. Kepler 22b sits in its star's habitable zone, receiving warmth, and it keeps its secrets quietly. Then there is Kepler 186f, discovered in 2014, and significant for a different reason entirely. Where Kepler 22b is larger than Earth, Kepler 186f is almost exactly our size, just 1.17 times Earth's radius. That made it the first Earth-sized planet ever found within a habitable zone, which felt, to many scientists and to many dreamers, like a genuine milestone. It orbits a red dwarf star about 580 light-years away. Red dwarfs are smaller and dimmer than our Sun, burning cooler and slower, and Kepler 186f sits at the outer edge of its star's habitable zone. It receives only about a third of the solar energy that Earth receives from the Sun. That means it would need a substantial greenhouse atmosphere, something rich in carbon dioxide, to trap enough warmth to keep any water liquid on its surface. Whether it has that atmosphere, we do not yet know, but the shape of it, the size of it, the address of it in its solar system, all of that felt like something. A first glimpse of a world that could, under the right conditions, be a little like home. Closer to home, in cosmic terms at least, is Proxima Centauri b. This one sits just 4.2 light-years away, which makes it our nearest known exoplanet, orbiting the closest star to our own Sun, a dim red dwarf called Proxima Centauri. It was found in 2016, and it is rocky, with a mass just slightly larger than Earth's. It orbits well within its star's habitable zone. On paper, that sounds promising. But Proxima Centauri is not a gentle star. It is active and temperamental, prone to powerful stellar flares, sudden bursts of radiation and energy that sweep outward and, over time, can strip away a planet's atmosphere entirely. Whether Proxima Centauri b still has enough of an atmosphere to hold liquid water, or whether those flares have worn it away over billions of years, remains one of the more pressing questions in astrobiology. Still, it is there. The nearest star to us has a planet in its habitable zone. That thought alone is worth sitting with for a moment. 4.2 light-years. Impossibly far for us now, but our nearest cosmic neighbor has a world in just the right place. And then there is the most extraordinary discovery of all in this particular chapter of our story, the TRAPPIST-1 system. In 2017, astronomers announced something that had never been seen before. 7 planets, all roughly Earth-sized, all orbiting a single small, ultra-cool star. And that star is just 40 light-years away, which in galactic terms is practically next door. 3 of those 7 worlds sit within the habitable zone. They are known as TRAPPIST-1e, TRAPPIST-1f, and TRAPPIST-1g. Of these, TRAPPIST-1e draws the most attention. Its density suggests a rocky composition not unlike our own Earth. It is the kind of world where, if the conditions are right, if the atmosphere holds, if the chemistry cooperates, liquid water could exist. The TRAPPIST-1 system has become a kind of laboratory for scientists thinking about habitability, because with 7 planets so close together, their gravitational relationships are complex and fascinating. They tug at one another as they orbit, and those tugs maintain a kind of rhythm, a gravitational dance called orbital resonance, that keeps their paths stable and their interiors warm. More recently, the James Webb Space Telescope has been studying TRAPPIST-1e with extraordinary care. In late 2025 and into 2026, it found hints of a possible atmosphere around the planet. Not the original primordial one, which was likely stripped away long ago, but perhaps a secondary atmosphere, a newer one, born from volcanic activity and internal processes. A secondary atmosphere, more stable, more Earth-like in its origins. That is a remarkable thing. A planet rebuilding itself, losing one sky, and, over billions of years, quietly making another. I find that quietly moving, the persistence of it, the way that even harsh conditions, even the stripping away of something as fundamental as an atmosphere, might not be the end of the story. Let yourself breathe with that for a moment. These worlds are out there right now, in the dark, orbiting their stars. Some are ocean-wrapped mysteries. Some are cold and windswept at the edges of warmth. Some are close enough to their stars to feel their tempers, and some are tucked into a system with 6 siblings, all in a slow and ancient dance. None of them knows we are watching. None of them knows that here, on a small, rocky world 40 light years away, someone is lying in bed, thinking about them. What a beautiful thing that is. To reach across that distance, not in a ship, not even with sound, but just with light and mathematics and the quiet ambition of human curiosity. Rest into that. Let the distances wash over you. You do not have to hold all of it. Just let it be large and let yourself be small within it. And notice how comfortable that can feel. The universe is very old and very wide, and it is full of worlds in the right kind of places. Tonight, from your bed, you are one of the creatures lucky enough to know that, the planet that keeps its thermostat on. There is something deeply comforting about the idea of a thermostat. That quiet, invisible mechanism that notices when a room gets too cold and gently warms it. That notices when it gets too warm and eases back. Most of us have one somewhere in our homes, and we rarely think about it. It just works, steadily and without drama, keeping things just right. Earth has one too. It is not a small box on a wall. It is a planetary-scale chemical cycle, billions of years old, woven into the rock and rain and ocean and deep interior of our world. Scientists call it the carbonate-silicate cycle, and it is one of the most important reasons life has been able to persist here for so long. Let me walk you through it gently, because it is one of those ideas that, once you understand it, makes the world feel almost miraculous. there is less, it cools. On its own, that there is less, it cools. On its own, that sounds unstable, a planet at the mercy of however much carbon dioxide happens to be around. But the carbonate-silicate cycle is what keeps it in check. Here is how it works. When carbon dioxide in the atmosphere meets rainwater, the two combine to form a weak acid, carbonic acid. That acid falls to the surface and slowly, over long spans of time, reacts with rocks. Silicate rocks, the kind that make up so much of Earth's crust. The acid weathers the rock, breaking it down, releasing calcium and bicarbonate ions into the water, which rivers then carry to the sea. In the ocean, tiny marine creatures, shells and corals and microscopic organisms take up those calcium and bicarbonate ions and use them to build their shells, their structures, their homes. When those creatures die, they sink to the sea floor, and their shells accumulate as sediment, layer upon layer, over millions of years, becoming limestone and other carbonate rocks. And then the deep earth does something extraordinary. Plate tectonics, the slow grinding movement of the crust, carries those seafloor sediments down into the mantle, deep below the surface, where the heat and pressure are immense. Down there, the carbonate rocks break apart, releasing carbon dioxide again, and that carbon dioxide works its way back up through the crust, through volcanic activity, and returns to the atmosphere. The cycle is complete. Carbon goes in, carbon comes out, rock to ocean to mantle to sky and back again. But here is the beautiful part, the part that makes it a thermostat rather than just a cycle. It is sensitive to temperature. When the climate warms, rainfall increases. More rain means more weathering of rocks. More weathering means more carbon dioxide is pulled from the atmosphere. Less carbon dioxide means less greenhouse warming. The planet cools. When the climate cools, rainfall decreases, less weathering happens. Carbon dioxide from volcanoes accumulates in the atmosphere without being drawn down as quickly. Greenhouse warming increases, the planet warms, the cycle self-corrects. It is not instant, it works over millions of years rather than decades. But over geological time, it is remarkably effective. It has kept Earth within a range suitable for liquid water for something close to 4 billion years, even as the sun has gradually brightened over that same period. That last detail is worth pausing on. Our sun is not the same star it was when life first appeared on Earth. It has been slowly growing more luminous over billions of years. Early in Earth's history, the sun was roughly 30% dimmer than it is today. And yet, the geological record shows that liquid water existed on Earth's surface even then. Rivers ran, oceans formed, life began. This creates what scientists call the faint young sun paradox. If the early sun was so much dimmer, how was Earth warm enough to avoid being a frozen ball of ice? For a long time, researchers suspected the answer might involve greenhouse gases produced by intense space weather, things like nitrous oxide generated by powerful solar storms in the sun's turbulent youth. A study published in December 2025 tested this idea very carefully and found that it does not quite work. The amounts of warming gas produced by those early solar storms were simply too small to make a meaningful difference, less than a fraction of a degree of warming in total. The paradox, it seems, remains open. The full answer is still waiting to be found. What we do know is that the carbonate-silicate cycle was a key part of keeping early Earth habitable, drawing down carbon dioxide when things warmed, letting it build when things cooled. The thermostat was always there, always working, even when the star itself was changing. Now, for a long time, scientists assumed that this kind of cycle required plate tectonics. The movement of crustal plates is what carries seafloor sediments into the mantle and allows carbon to be recycled back into the atmosphere. Without it, you might expect the cycle to break down, the thermostat to stop working. But more recent research, carried through 2025 and 2026, has begun to challenge that assumption. It appears that even planets with what is called stagnant lid tectonics, where a single unmoving plate covers the entire mantle like a shell, might still be able to support life if they have enough volcanic activity to keep outgassing carbon dioxide. The thermostat might work differently on such worlds, but it might still work. That opens the door a little wider. It means that the kind of geological activity needed to sustain a habitable climate might come in more varieties than we previously thought. There is another piece of this story worth settling into as you lie there in the quiet. The magnetic field. Earth has one. It is generated by the movement of liquid iron in our planet's outer core, a vast dynamo spinning and shifting, producing a magnetic field that extends thousands of kilometers into space. That field deflects the solar wind, the constant stream of charged particles flowing outward from the sun. Without it, those particles would batter the upper atmosphere continuously, gradually stripping away lighter gases, including water vapor. Over billions of years, this erosion can be devastating. Mars, which appears to have lost its global magnetic field long ago, also appears to have lost much of its atmosphere, and with it, its liquid water. A world that once may have had rivers and oceans became cold and thin-aired and dry. The magnetic field is not separate from the story of habitability. It is part of the same interconnected system. The core generates the dynamo. The mantle drives the convection that keeps the core active. The crust recycles carbon through tectonics. The atmosphere holds warmth. The ocean moderates temperature. All of it linked, all of it working together. A living planet is not just a rock in the right orbit. It is a system, a beautifully balanced, self-regulating, interconnected system that has been quietly maintaining itself for longer than any of us can truly imagine. And here you are, resting on the surface of it, breathing its air, warmed by its regulated climate, protected by its invisible magnetic shield. The thermostat is on. It has been on for 4 billion years, and tonight at least, everything is just right. Let that settle into you as you breathe. The hum of the planet beneath you, doing its slow and patient work. You are held by systems so large and so ancient, they make the span of a human life feel like the briefest, most tender flicker. And yet that flicker is yours. Rest in it. A smell of rain and ancient stone. There is a word for the smell of rain on dry earth, petrichor. It is one of those words that feels like the thing it describes, warm and earthy and deeply familiar. That smell comes partly from oils released by plants and rocks, and partly from a compound produced by bacteria in the soil. It is, in a very literal sense, the smell of the earth being alive. I mention it because tonight we are going to think about water. Not just water as a fact of chemistry, but water as the thread that connects everything. The reason scientists look where they look and hope what they hope. We talked in our last section about how the carbonate-silicate cycle keeps Earth's temperature regulated over millions of years. But underpinning all of that, the reason any of it matters is water itself. Liquid water. The thing the Goldilocks zone is really all about. Water is an almost unreasonably useful molecule. It remains liquid across a wide range of temperatures. It expands when it freezes, which means ice floats, which means frozen lakes develop a layer of ice on top that insulates the liquid water beneath, allowing life to survive through winter. It carries heat efficiently, helping to moderate temperature across a planet's surface. It is an extraordinary solvent, dissolving more substances than almost any other liquid, which is precisely why it can carry nutrients, facilitate chemical reactions, and allow the machinery of biology to function. Life as we know it did not just happen to evolve in water. Life as we know it is built from processes that fundamentally require water to operate, which is why, when we search for life elsewhere, we search for water first. But here is something that has shifted quietly in recent years. For a long time, when scientists talked about the search for liquid water, they meant liquid water on a surface, a planet with oceans, lakes, rivers, something we could imagine standing beside. Increasingly, that picture has expanded because it turns out that liquid water can exist in places far removed from the cozy band of the Goldilocks zone and in forms we might not immediately recognize. Take Europa. It is one of Jupiter's moons, and it sits far outside what we would traditionally call the habitable zone of our sun. It is cold, its surface is covered in ice, and yet beneath that ice, kept warm not by sunlight, but by the tidal forces of Jupiter's immense gravity pulling and flexing the moon's interior, there is a liquid water ocean, a real one, possibly deeper than any ocean on Earth. The gravitational relationship between Europa and Jupiter generates heat inside the moon, the way kneading dough generates warmth in your hands. That heat keeps the interior liquid, and a liquid water ocean, even in the dark, even under ice, even 628 million kilometers from the sun, is considered one of the most promising places in the solar system to look for microbial life. Enceladus, one of Saturn's moons, tells a similar story. It is small, bright white, and very cold on its surface. But its interior is warm, again from tidal heating, and the evidence for its subsurface ocean is even more dramatic than Europa's. Enceladus has geysers. great plumes of water vapor and ice particles erupting from cracks near its south pole, spraying material out into space. The Cassini spacecraft flew through those plumes and detected water, organic molecules, and molecular hydrogen, all of the ingredients that on Earth support life in deep ocean hydrothermal vents. And then there is Titan, Saturn's largest moon, and perhaps the strangest habitable candidate of all. Titan has lakes, real liquid lakes on its surface. But they are not water. They are liquid methane and ethane, hydrocarbons that remain liquid at Titan's frigid surface temperature of around -179 degrees Celsius. Titan's atmosphere is thick, hazy, orange, and dominated by nitrogen, much like early Earth in some respects. Could life exist in liquid methane? It would have to be life utterly unlike anything we know. It would use different chemistry, different solvents, different processes entirely. But some researchers, Christopher McKay among them, have proposed the concept of a methane habitable zone, a region around a star where temperatures are cold enough for methane lakes to exist. For our Sun, that zone is centered at around 11 astronomical units, which is roughly where Saturn orbits. The idea that habitability might come in entirely different chemical flavors is one of the more mind-expanding thoughts in modern astrobiology. We call our Earth-centered view carbon chauvinism, a gentle self-criticism acknowledging that we tend to assume life must look like us, must use what we use. Perhaps it does not have to. And there is one more idea in this space that is so new it still feels slightly startling. A hypothesis from 2026 suggests that warm, rocky planets with very thin atmospheres might be able to support life using what are called ionic liquids. These are essentially liquid salts, substances that remain liquid at very high temperatures without evaporating, even in near vacuum conditions. If life could use ionic liquids as a solvent instead of water, then planets previously considered too hot for habitability might actually fall within a different kind of zone entirely. We do not know if this is true. It is a hypothesis, an idea being tested and explored. But the fact that it is being seriously considered tells you something about how much our understanding of what is possible has expanded. When the Goldilocks zone was first defined, it was a simple band around a star, a distance range. Now it is something much richer. A set of overlapping questions about pressure and chemistry and gravity and geology and the many different ways that a universe might, quietly and in its own time, permit life to happen. Think about what that means for a moment, gently, without straining. The universe may be full of oceans we will never see, tucked beneath the ice of moons, warmed by the pull of giant planets. It may harbor lakes of methane on orange-skied worlds where the sun looks small and distant. It may contain chemistry we have not yet imagined, running quietly in conditions we would find utterly inhospitable. And all of it, every possibility, every candidate, every moon and planet and distant world is following the same fundamental rules, the same physics, the same chemistry. The universe is consistent in its laws, even when it is wildly creative in what it does with them. You are made of the same atoms as Europa's ocean, the same fundamental particles as Titan's methane lakes, the same stardust as every candidate world we have ever pointed a telescope toward. That is not a poetic flourish. That is chemistry. That is physics. That is the truth of the matter. Breathe it in, like petrichor on a warm evening, the smell of something alive in a universe that seems quietly, persistently, beautifully inclined toward life. Let your thoughts go wherever they would like now. There is no need to hold them tightly. Just drift the way water does, finding the path of least resistance, settling into whatever shape the night allows. You are doing so well. Rest is very close. The galactic sweet spot. We have been thinking about habitable zones around individual stars. That cozy band of space where a planet might hold liquid water regulated by atmosphere and geology and the steady warmth of its sun. But tonight I would like to zoom out, much further out, further than a single solar system, further than a neighborhood of stars, all the way out to the scale of an entire galaxy. Because it turns out the Goldilocks idea does not stop at the edge of a solar system, it applies to galaxies too. Our galaxy, the Milky Way, is a vast spiral structure containing somewhere between 100 and 400 billion stars. If you could see it from above, you would see great curving arms of stars and gas and dust wrapping around a bright, dense central region. That center, the galactic core, is extraordinarily active. There are ancient star clusters there, enormous concentrations of stellar mass, and at the very heart of it all sits a supermassive black hole. Now, you might think that the center of the galaxy, with all those stars so close together, would be the best place for life. More stars means more planets, and more planets means more chances. But proximity comes with a cost. The galactic center is a violent place. Stars are born and die there at enormous rates, and when massive stars die, they do not go quietly. They explode as supernovae, releasing staggering amounts of energy and radiation. A supernova close enough to a planet can strip away its atmosphere, damage its chemistry, irradiate its surface. Too many of those events, too close together, and habitability becomes very difficult to maintain. On the other hand, move too far from the galactic center toward the very outer edges of the Milky Way, and a different problem emerges. The outer galaxy is poor in what astronomers call metallicity. In astronomy, that word has a specific meaning. It refers to all elements heavier than hydrogen and helium. Carbon, oxygen, iron, silicon, the building blocks of rocky planets and complex chemistry. The outer galaxy has fewer of those heavier elements because they are forged in stellar interiors and distributed by supernovae, and there has simply been less of that activity out there. Without enough of those heavier elements, rocky planets are harder to form. And without rocky planets, the kind of stable surface environments that complex life seems to require become much rarer. So the galactic center has too much violence. The outer edges have too few ingredients, and in between, there is a sweet spot. This idea was proposed in 2001 by three researchers, Guillermo Gonzalez, Donald Brownlee, and Peter Ward. They called it the galactic habitable zone, and they estimated it to be an annular region, a ring sitting somewhere between roughly 7 and 9 kiloparsecs from the center of the Milky Way. Our solar system sits at approximately 8 kiloparsecs from the galactic center, right in the middle of that estimated range. We are, it seems, in the Goldilocks zone of the Milky Way itself. Conditions for life seem to have required not just one fortunate circumstance, but a kind of nested luck. The right star in the right part of the galaxy, with the right planet at the right distance. Or perhaps it is not luck at all. Perhaps the galactic habitable zone is simply where the conditions for making life have had the most time and the best ingredients to work with, and our being here is, in a sense, inevitable given where we are. Life arose here because this is the kind of place where life can arise. Now, 2026 has brought some extraordinary new developments to this broader picture. The James Webb Space Telescope, which has been transforming our understanding of exoplanets and distant systems, has been doing remarkable work. In February of 2026, just weeks ago as this was written, 21 new planets were added to NASA's exoplanet archive in a single day. Among them were 4 new worlds in a system called LHS 1903. Scientists believe those planets formed through what they describe as an inside-out process, beginning close to their star and building outward over time. That sequence of formation may influence how much water and other volatile compounds those planets retained, and therefore whether any of them might be habitable. Another candidate, designated HD 137010b, is an Earth-sized planet orbiting a star somewhat smaller than our Sun, about 146 light-years away. Its orbital period, the length of its year, is estimated at somewhere between 300 and 550 days, placing it near the outer edge of its star's habitable zone. It is a primary target for upcoming spectroscopic study, where scientists will look for signs of an atmosphere rich enough in greenhouse gases to keep any surface water liquid at that distance. And then there is the HR 8799 system, where JWST spectral data released in early February 2026 detected sulfur and other heavy elements in the atmospheres of directly imaged giant planets. Those planets are themselves far too large and too distant from their star to be habitable. But the presence of those heavier elements tells scientists something important about the metallicity of the whole system, and whether smaller, rocky, habitable zone planets might eventually be found there too. The pace of discovery has become genuinely breathtaking. There was a time not long ago when we did not know with certainty that any other star had planets at all. The first confirmed detection of an exoplanet orbiting a sun-like star came only in 1995. That is within living memory for many people listening tonight. In just 3 decades, we have gone from that single discovery to an archive of thousands of confirmed worlds, with more arriving almost daily. And JWST is doing something that previous telescopes could only gesture toward. It is beginning to read the atmospheres of some of these worlds. It does this through spectroscopy, spreading the light of a star into its component wavelengths and looking for the fingerprints of specific molecules. When a planet passes in front of its star, a tiny fraction of the starlight filters through the planet's atmosphere, and different gases absorb different wavelengths. By studying those patterns, scientists can begin to identify what an atmosphere is made of. For TRAPPIST-1e, that process has revealed hints of a possible secondary atmosphere, as we discussed earlier. But the same technique has also been applied to a world called K218b, and what was found there is perhaps the most tantalizing and controversial result in recent exoplanet science. K218b is a planet about 124 light-years away. It is significantly larger than Earth, about 8.5 times our mass, and it orbits within its star's habitable zone. JWST observations detected methane and carbon dioxide in its atmosphere, and a notable absence of ammonia. That chemical profile is consistent with what scientists call a Hycean world, a planet with a hydrogen-rich atmosphere sitting above a global liquid water ocean. But there was something else in the data, a tentative signal, fragile and debated, for a molecule called dimethyl sulfide. On Earth, dimethyl sulfide is produced almost exclusively by marine life, by phytoplankton, microscopic ocean organisms going about their quiet biological business. It is, in the language of astrobiology, what is called a biosignature, a potential sign of life. I want to be careful here because the science is careful. The signal was detected at what researchers call a 3 sigma confidence level in April 2025, meaning there was roughly a 0.3% chance it was a fluke. By July 2025, after more analysis, that confidence had actually decreased slightly to 2.7 sigma, still below the 5 sigma threshold that scientists require before they will call something a confirmed detection. And there is another complication. Laboratory experiments have shown that dimethyl sulfide can be produced abiotically, without any biology at all, in hydrogen-rich atmospheres exposed to starlight. So the signal, even if it is real, does not necessarily mean life. It means something interesting is happening in that atmosphere, and we do not yet know what. That is where the science sits right now. Not a discovery, not a confirmation, a question held very carefully, being examined with great patience and great precision. There is something I find deeply restful about that kind of careful, unhurried inquiry. No rush to conclusions, no leap before the evidence is ready, just steady, patient looking, asking the question again and again with better tools each time. That is, in its own way, a kind of wisdom. Let your mind wander into that vastness for a moment. Thousands of worlds in our catalog, with more arriving every day. one galaxy among hundreds of billions, a galactic habitable zone within which our own small star happens to sit. We are not at the center of the universe. We are not even at the center of our galaxy. We are in a quiet, well-positioned neighborhood on a small and fortunate planet, and we have developed the curiosity and the instruments to reach outward and ask whether anyone else might be out there, somewhere, in their own just right place. That reaching is one of the most beautiful things our species does. Let it carry you gently now as your breathing slows and the night deepens. You are part of that reaching just by being curious, just by listening, just by being here. The galaxy is very large. The night is very quiet, and you are exactly where you need to be. A gentle thought before we continue. Before we drift into our next chapter, I just wanted to take a quiet moment to mention something that might be helpful. If sleep is something you struggle with regularly, if nights like this one feel familiar, lying awake when you wish you weren't, then it might be worth taking a look in the description below this video. I sometimes share things there that I think could genuinely help. Books, products, a little bit of guidance, nothing pushy, nothing overwhelming, just a few gentle suggestions from someone who understands that sleep does not always come easily. Have a look when you get a chance. It might just have something that helps. Right then, let us continue our journey. The twilight ring and the eyeball worlds. I want to paint you a picture. Imagine a planet where one side is always day and the other is always night, where the sun never moves in the sky, hanging permanently above the same point on the surface, blazing down for billions of years without pause. And on the opposite side, a darkness just as permanent, cold and still and ancient. This is not science fiction. These worlds almost certainly exist, and they are among the most fascinating and counterintuitive places in our catalog of candidates for life. They are called tidally locked planets, and they form almost exclusively around a particular kind of star. Red dwarf stars, the smallest and dimmest category of star, are by far the most common type in the galaxy. Estimates suggest that around 70% of all stars are red dwarfs, and because they are dim, their habitable zones sit very close in, much closer than Earth sits to our sun. A planet in a red dwarf's habitable zone might orbit its star in just a few weeks, or even just a few days. Orbit that close, and the star's gravity does something powerful. It locks the planet's rotation to its orbit, the same way our moon is locked to Earth, always showing us the same face. The planet stops spinning freely and settles into a permanent arrangement. One face toward the star, one face away. For a long time, scientists considered this a serious problem for habitability. The day side would be scorched, potentially too hot for liquid water. The night side would be frozen, cold enough to lock away any atmosphere as ice. And without a full atmosphere, the planet could not regulate its temperature and habitability would collapse. But as climate modeling has grown more sophisticated using powerful three-dimensional simulations of planetary atmospheres, A more nuanced and rather wonderful picture has emerged. The most habitable region on such a world might not be the sunlit face at all. It might be the terminator, that thin, curving band that runs between permanent day and permanent night, where the sun sits perpetually on the horizon, neither fully risen nor fully set. A world of endless twilight stretching in a ring around the entire planet. Scientists sometimes call these eyeball planets because, viewed from space, a tidally locked world with a bright central region, a dark outer region, and a ring of twilight in between looks somewhat like a vast eye staring outward into the cosmos. Side would arrive there, moderated by the side would arrive there, moderated by the journey. The permanent horizon sun would provide gentle, consistent light. If water exists on such a world, the terminator zone might be where it pools, where it flows, where it persists. There is an even more intriguing mechanism that researchers have identified for certain tidally locked worlds. On planets with limited water, the dry, scorching day side can become so hot that it creates powerful atmospheric circulation, drawing air from the cooler regions toward the substellar point, the spot directly beneath the star. But on the night side, glaciers can form, vast sheets of ice accumulating in the permanent cold. And here is the part that feels almost poetic. Those glaciers are not static. Ice flows. Under its own weight, glacier ice moves slowly toward lower ground, toward the terminator. And as the ice crosses that boundary into the twilight, it encounters slightly warmer conditions and begins to melt. In an otherwise arid landscape, the terminator zone could be fed by a slow, steady supply of meltwater creeping in from the frozen night side. A river fed by a glacier that never stops in the perpetual twilight of a world that never turns. I find that image genuinely beautiful. The universe finding a way, as it so often seems to, around what first appeared to be an obstacle. There is a related idea that is even stranger, and I want to share it with you because it upends something that might seem obvious. You might assume that a more active, more energetic star is better for a planet in its habitable zone. More energy means more warmth, and warmth is good, right? Not always. On the early Earth, our young sun produced intense bursts of radiation and energetic particles. Coronal mass ejections and solar energetic particle events, the kind of space weather that makes the northern lights here on Earth. For a while, scientists hoped that this intense early activity might have helped warm the young Earth enough to keep liquid water flowing through the production of greenhouse gases like nitrous oxide. A careful study published in December 2025 tested this idea thoroughly and found that it simply does not work. The warming effect from those space weather-produced gases was smaller than 1/3 of a degree, barely anything, and strikingly, the same intense solar activity applied to a modern Earth-like atmosphere would actually cool the planet by around 3 degrees, not warm it. So intense stellar activity is not the warming friend it was hoped to be. In fact, for planets around the most active red dwarf stars like Proxima Centauri, that constant barrage of radiation and flares is one of the most serious threats to atmospheric retention. The very stars whose habitable zones are easiest to study because their planets orbit so close and transit so frequently are also the stars most likely to be actively stripping their planets' atmospheres away. That tension sits at the heart of a lot of current research. Red dwarfs are common, their habitable zones are accessible, their planets are detectable, and yet they are fierce, they flare, they radiate, and the planets closest to them pay the price. Unless, of course, those planets have found a way around it. Some researchers have suggested that certain tidally locked planets go through what are called episodic atmospheric collapses, where the atmosphere essentially freezes out onto the cold night side during periods of intense stellar activity, protecting the volatile gases from being stripped away by radiation. Then, when conditions ease, an asteroid or comet impact could reinflate the atmosphere, vaporizing the ices and returning gas to the sky. A planet breathing in and out over millions of years, collapsing and rebuilding, hiding its atmosphere in ice when the star rages, then thawing it out again when calm returns. It is a strange kind of resilience, not the steady, reliable stability of Earth, but a more dynamic, more precarious kind of persistence. And yet, according to modeling from 2025, planets like this might actually spend between 70 and 80% of their existence with a detectable atmosphere. That is more than enough time for life to get started if the conditions are otherwise right. The universe, it turns out, offers many different ways to stay alive. Stability is one path. Resilience through change is another. There is something in that worth sitting with, I think. Not just as a fact about distant planets, but as a thought to carry quietly. The conditions for life are not always ideal. Sometimes an atmosphere collapses and rebuilds. Sometimes the warmth comes not from a sun, but from the grinding of gravity deep inside a moon. Sometimes the habitable place is not the obvious one, not the bright center, but the quiet ring of twilight at the edge of the light. Life, or the possibility of it, finds the places that work, even the unlikely ones, even the ones that require a very specific and peculiar set of circumstances to align. As you lie there in your own particular quiet, in the specific warmth of your own bed, perhaps with light coming under a door somewhere, or the soft sound of the world outside continuing without you, you are in your own kind of Goldilocks condition. Not too much noise, not too much light, temperature just about right. The circumstances of rest aligned. You have found your terminator zone, your ring of twilight. And sleep, like a glacier moving very slowly toward warmer ground, is on its way to you. Let it come. There is nothing to do now but wait and breathe and let the night do what the night does best. And so we rest. We have traveled quite a distance tonight, you and I, from the simple, beautiful idea of a zone around a star where things are just right, all the way out to the scale of galaxies, to moons with hidden oceans, to worlds of endless twilight, where glaciers feed rivers that no one has ever seen. We thought about the carbonate silicate cycle, that ancient planetary thermostat, quietly keeping Earth livable for billions of years. We visited Kepler 22b and Kepler 186f, TRAPPIST 1, and Proxima Centauri b. We wondered about methane lakes on Titan and salt oceans on worlds too hot for water. We thought about a possible biosignature on a distant planet, held carefully and patiently by scientists who know that the best questions deserve the most careful answers. And through all of it, the thread running quietly underneath was this. The universe seems, in its own unhurried way, to be rather good at finding the conditions for life, not just here, not just in our particular sweet spot around our particular star, in our particular neighborhood of the Milky Way, but in unexpected places, through unexpected mechanisms, in forms we are only beginning to imagine. That is a thought worth carrying into sleep. Not with any urgency, not as something to solve or to worry over, but simply as a companion, a gentle reminder that the cosmos is vast and patient and full of possibility, and that somewhere out there, right now, other worlds are orbiting their stars, some of them perhaps in just the right place, with just the right kind of sky. And here you are on one of them. The music is going to carry you from here. There is nothing more you need to do or think or hold on to. Just let your mind do whatever it would like to do. Follow a thought if one comes, or follow nothing at all. Let the sounds wash over you and under you and through you. You came here tonight because sleep felt far away, and I hope it feels a little closer now. I hope the distances we traveled together made the space inside your own mind feel a little wider and a little quieter. Thank you so much for being here. Thank you for listening. If tonight helped you, even a little, please do consider leaving a like, and subscribing means that the next time sleep feels difficult, we will be here waiting for you. Sleep well. You are on a planet in the Goldilocks zone, wrapped in a magnetic field, warmed by a regulated climate, held gently by gravity. Everything tonight is just right.